Abaqus Standard to Abaqus Explicit Co-Simulation provides a cost-effective method for analyzing complex models in which different model regions can benefit from the respective strengths of Abaqus Standard and Abaqus Explicit. For example, in this truck crash simulation, the high-speed dynamic response and complex contact conditions that occur in the truck's front end and tires must be modeled with Abaqus Explicit. However, many of the components in the rear of the truck only experience small strains during the impact. These components are most efficiently modeled with Abaqus Standard. To improve performance even further, some of the Abaqus Standard structures are modeled as substructures. More than 1/4 of the runtime for this analysis is saved by using the co-simulation technique, rather than analyzing the entire truck with Abaqus Explicit. The savings is a bit less if detailed results are extracted from the substructures. In this demonstration, I will show you how to convert this simple beam impact simulation, originally modeled with Abaqus Explicit alone, into a co-simulation. In the co-simulation, the root of the beam will be modeled with Abaqus Standard, while the impact zone and the beam tip will be modeled with Abaqus Explicit. Notice that separate parts have been used for the portions of the beam to be modeled with Abaqus Standard and Abaqus Explicit. This is required for co-simulation modeling. I will begin by copying the complete model twice. Once to create a model for the Abaqus Standard portion of the co-simulation, and once to create a model for the Abaqus Explicit portion of the co-simulation. In the Abaqus Explicit model, I will select the beam root part instance. This instance will not be a part of the Abaqus Explicit portion of the simulation, so I will link it to the Abaqus Standard model. This way, any changes I make to the parent part in the Abaqus Standard model will be visible in the Abaqus Explicit model, allowing me to verify that my co-simulation models match up properly. I will also exclude the beam root part instance from the Abaqus Explicit simulation. Notice that the excluded part instance appears as dark gray in the viewport. In addition, icons in the model tree indicate that the part has been excluded and linked. Switching to the Abaqus Standard model, I will select the beam tip and impactor part instances and link them to the Abaqus Explicit model. I will exclude these instances from the Abaqus Standard portion of the simulation. Next, in the Abaqus Standard model, I will replace the existing explicit dynamic step with an implicit dynamic step. The time period for the analysis will be 0.3 seconds. I will not include nonlinear geometric effects because the behavior of the beam root is linear. I will increase the maximum number of increments allowed for the step. I will specify an initial increment size and the half-step residual tolerance. Next, in the Abaqus Standard model, I will suppress items that are not appropriate for the Abaqus Standard portion of the simulation. I will suppress the history output for the beam tip. I will suppress the predefined field for the initial impactor velocity. I will suppress the rigid body constraint that makes the impactor rigid. I will suppress the tie constraint which tied the two halves of the beam together for the pure Abaqus Explicit simulation. Returning to the Abaqus Explicit model, I will again suppress the tie constraint, which held the two halves of the beam together for the pure Abaqus Explicit simulation, and I will suppress the boundary condition on the fixed end of the beam. Next, I will create co-simulation interactions to couple the two models together. I will begin by creating the interaction in the Abaqus explicit model. I will select Step 1 and choose the co-simulation interaction type. I will use a surface for the interaction. Before selecting the surface, I will use display groups to remove the beam root modeled with Abaqus Standard. Now I can easily select the surface on the beam tip that connects to the beam root. In the interaction editor, I will select the lockstep incrementation option. The lockstep incrementation method will force Abaqus Standard to match the Abaqus explicit increment size. The advantages to this method are that it has low memory requirements and that displacements on either side of the interface will be identical. The disadvantage is that Abaqus Standard must use small time increments, which is not an issue in a model as small as this, but on larger, more typical co-simulation applications, this may not be desirable. The alternative is to use the subcycling incrementation method, which allows Abaqus Standard and Abaqus Explicit to proceed using their natural time increment sizes. With this method, you can take advantage of large Abaqus Standard time increment sizes. However, at the interface, you may notice some drift and displacement, since this method works by enforcing velocity compatibility across the boundary, rather than displacement compatibility as in the lockstep method. The other disadvantage of the subcycling method is that the computations required for the information transfer across the boundary can be expensive, particularly if the number of nodes on the interface is large. Therefore, I recommend the subcycle method for co-simulations with relatively few nodes at the interface. If there are a large number of interface nodes, the lockstep method may be more efficient. The other setting in the co-simulation interaction editor allows you to specify a coupling step period. However, I strongly discourage you from doing so, since this time period will dictate the Abaqus explicit time increment size, which could result in an unstable Abaqus explicit solution if the specified increment size is larger than the stable time increment size. Now that the co-simulation interaction is defined in the Abaqus explicit model, I will create an equivalent interaction in the Abaqus Standard model. In this case, I will choose a node type interaction region, since I have already defined a set on the interface side of the beam root. If I had defined a surface in advance, I could have used a surface type interaction region. This choice is purely based on convenience. The incrementation method must be the same for both the Abaqus Standard and Abaqus Explicit co-simulation interaction definitions. Hence, I will select the lockstep method. The co-simulation cannot be submitted using regular analysis jobs. To run a co-simulation, I must create a co-execution. In the co-execution editor, I will select the two co-simulation models. Abaqus lists the default job names for the models, which can be modified. The initial options for the analysis jobs can be specified using the Job Parameters tab. In this case, I will choose Double Precision for the Abaqus Explicit analysis. Double Precision is recommended for co-simulations. Once the co-execution is created, I can review, and if necessary edit, the properties for the individual Abaqus Standard and Abaqus Explicit jobs. I can also use these jobs to write input files or to perform data check analyses. Once I submit the co-execution, the individual jobs can be monitored. Co-execution results are written to two separate output database files, one for the Abaqus Standard portion of the simulation and one for the Abaqus Explicit portion of the simulation. They can be viewed together by creating an overlay plot. I will create the first layer using the Abaqus explicit portion of the model. Then I will switch to the Abaqus standard output database to create the second layer. For this layer, I will copy the view from the original layer. This is required to synchronize the local coordinate systems of the two layers so that the two halves of the model will match up. Now that I have created the two layers, I will create the overlay plot. Notice that the Abaqus standard and Abaqus explicit portions of the model don't appear to line up exactly, which is surprising since I used the lockstep integration method. The reason for this is that the Abaqus standard portion of the model was analyzed without including nonlinear geometric effects. The deformation scale factor for this portion of the model, therefore, is scaled so that small displacements will be visible. In the Overlay Plot Layer Manager, I will choose to apply Plot State and Plot Layer options to all the layers simultaneously. This in itself does not synchronize the plot state and plot options for the two layers, but it does ensure that when I go ahead and specify a deformation scale factor of 1, it is applied to both layers. Now that I've seen the final deformed shape of the model, I would like to animate the results. Notice that initially, Abaqus only animates the current layer of the overlay plot. To animate both layers simultaneously, I must access the animation options, select the Viewports tab, and activate both layers to synchronize the animations of the two output database files. Now I will create a contour plot of the results. While the contour plot state is applied to both layers of the overlay plot, thanks to the settings in the Overlay Plot Manager, the contour legend is only shown for the current layer. I will use the contour plot options to set plot limits. With limits set, consistent contour values are applied to both halves of the model. Here is a summary of the Abaqus CAE co-simulation workflow. Pause this demonstration if you would like to study it in detail.